Hello everyone, Gautam here from SoftTech Explorer, and welcome back to the channel. Today, we're diving deep into a component that's absolutely fundamental to almost every piece of tech you own. Yet it often lives in the shadows, unnoticed. Think about the last time you bought a new phone or a laptop. You probably looked at the screen size, the camera quality, maybe the processor's speed, right? But how much thought did you give to its RAM? For many, it's just a number on a spec sheet. 8 gigabytes, 16 gigabytes, maybe 32 gigabytes if you're a power user. It's one of those things we know is important, but the why and how can feel a bit like a black box. This component is the silent workhorse, the unsung hero that makes your digital life smooth, fast, and possible. This hero is called DRAM, or Dynamic Random Access Memory. It's the short-term memory of your device, the digital workspace where all the magic happens. Every app you open, every tab you have running in your browser, every document you're editing, it all lives inside this temporary space. Without DRAM, your powerful processor would be like a master chef with no countertop to prepare the food. It would have all the skills but nowhere to work. The speed at which you can switch between apps, the number of tasks you can juggle simultaneously, all of this is directly tied to the performance and capacity of your DRAM. It's the critical link that keeps everything flowing seamlessly, preventing your digital experience from becoming a frustrating, laggy mess. So what exactly are we going to explore in this series? We're going on a complete journey, from the absolute basics to the intricate details of how this technology functions. We'll start by understanding what makes DRAM dynamic and why that little detail is so crucial. We'll then travel back in time to uncover its fascinating history, looking at the brilliant minds and the key breakthroughs that made it the powerhouse it is today. We'll break down the core components, the tiny transistors and capacitors that hold your data one bit at a time. It's a story of incredible engineering, fierce market competition, and constant innovation that has shaped the world of computing as we know it. Our goal is to demystify this essential piece of technology. By the end of this deep dive, you won't just see RAM as a number anymore. You'll understand the physics behind it, the economics that drive its production, and its pivotal role in everything from your smartphone and gaming console to the massive supercomputers pushing the boundaries of science. We'll make the complex simple and the technical accessible. So, whether you're a computer science student, a tech enthusiast, or just someone curious about what makes your gadgets tick, you're in the right place. Let's get ready to pull back the curtain on the unsung hero of our digital world. To truly appreciate DRAM, let's first take a step back and think about memory in a more general sense. In our everyday lives, we rely on different kinds of memory constantly. You have your long-term memory, where you store important facts like your own name or the capital of India. This is like the hard drive or SSD in your computer. It's for permanent storage. Then you have your short-term or working memory. Imagine you're cooking a new recipe. You read a step, say add 2 spoons of turmeric powder, and you hold that instruction in your mind just long enough to do it. You don't need to remember it forever, just for the immediate task. This is precisely the role DRAM plays in your computer. This concept of a temporary workspace is vital for any complex task. Think about it. When you're working on a math problem, you jot down numbers and intermediate calculations on a rough sheet of paper. You don't carve them into a stone tablet. That rough sheet is your temporary workspace. It's fast, easy to access, and you can erase and rewrite things quickly. Once you have the final answer, you might write it down neatly in your main notebook. Your computer does the exact same thing. The CPU, or the brain of the computer, pulls the necessary data from the slow, permanent storage, your SSD, and loads it into the super-fast temporary workspace, your DRAM, to actively work on it. This is why opening a large application or a big file takes a moment. That's the loading process. The importance of this rough sheet cannot be overstated. Imagine if your computer had to go back to its main storage for every single tiny calculation or piece of data it needed. It would be incredibly slow. It would be like a chef having to walk to a storeroom down the hall every time they needed a pinch of salt or a single onion. The kitchen would grind to a halt. DRAM is the chef's countertop, with all the ingredients and tools laid out, ready for immediate use. This is why adding more RAM to an older computer can often give it a new lease of life. It's not making the processor faster, but it's giving it a bigger, better organized workspace, allowing it to handle more tasks at once without getting overwhelmed. So, when we talk about DRAM, we're not just discussing a component, we're discussing the very foundation of modern multitasking and computing speed. It's the technology that allows you to listen to music, while writing an email with 20 browser tabs open in the background, all without your computer breaking a sweat. It's the bridge between the raw processing power of your CPU and the vast library of data on your storage drive. Understanding how this bridge is built, how it operates, and why it needs to be constantly refreshed is key to understanding the performance of nearly every digital device you interact with. In the next part, we'll start peeling back the layers and get into what DRAM really is. Alright, so we've established that DRAM is your computer's temporary workspace. It's short-term memory. But what does that name, Dynamic Random Access Memory, actually mean? Let's break it down, starting with the most important word here, dynamic. This isn't just a fancy marketing term, it gets to the very core of how this technology works. Inside a DRAM chip, every single bit of information, a 1 or a 0, is stored in a microscopic component called a memory cell. This cell is incredibly simple, consisting mainly of a tiny capacitor and a transistor. Think of the capacitor as a tiny bucket that can hold an electrical charge. If the bucket is full of charge, it represents a 1. If it's empty, it represents a 0. This is the fundamental principle of storing data in DRAM. Now, here's where the dynamic part comes into play. These tiny buckets, these capacitors, are not perfect. They have a small, unavoidable leak. The electrical charge that represents your data slowly seeps away, almost like water evaporating from a bucket on a hot day. If left on its own, a full bucket, a 1, would eventually become empty, a 0, and the data would be lost forever. This leakage is a natural characteristic of the components used. To prevent this from happening, the computer's memory controller has to constantly step in and check on these buckets. It has to read the data, see if a bucket is supposed to be full, and if it is, top it up with a fresh jolt of electricity. This process is called refreshing. This constant cycle of charge leak and refresh is what makes the memory dynamic. It's an active, ongoing process that happens thousands of times every second, completely behind the scenes, without you ever noticing. It's a fundamental trade-off. The simplicity of the memory cell, just one transistor and one capacitor, is what allows manufacturers to pack billions of these cells onto a single chip, making DRAM incredibly dense and relatively cheap. This is why you can get 16 gigabytes or 32 gigabytes of RAM in your laptop. The downside, however, is this constant need for power and refreshment. If you turn off your computer, the refreshing stops, the charge leaks away completely, and all the data in the DRAM is wiped clean. This is why it's called volatile memory. Contrast this with something like your computer's SSD or a USB pen drive. That's non-volatile memory. You can save a file, turn off your computer for a year, turn it back on, and the file will still be there. That technology stores data in a much more permanent way that doesn't require constant power to maintain. So, while DRAM is amazingly fast and perfect for active tasks, its dynamic and volatile nature means it's only suitable for temporary storage while the power is on. It's a high-speed, high-maintenance workspace, not a long-term storage library. This single characteristic, the need to refresh, defines DRAM and sets it apart from other types of memory we'll discuss later. So, we know DRAM is a temporary volatile workspace. But how does your computer actually use it in a practical moment-to-moment way? Let's walk through a simple everyday example. Imagine you decide to open a web browser, say Google Chrome, to watch a video on our SoftTech Explorer channel. The first thing you do is double-click the Chrome icon. At this moment, the icon is just a shortcut sitting on your permanent storage, your SSD. When you click it, your computer's operating system gets the instruction. It knows it needs to run the Chrome application. The processor, the brain of the operation, then fetches the essential files for the Chrome program from the slow SSD. This is where DRAM springs into action. The processor doesn't work with those files directly from the SSD. That would be far too slow. Instead, it copies all the necessary program code, user interface elements, and other required data into the DRAM. This is the loading screen you sometimes see when an application starts. It's the digital equivalent of a librarian going into the archives, finding the right books, and placing them on your desk for you to read. Once Chrome is loaded into DRAM, it runs incredibly fast. Every click, every new tab you open, every character you type in the search bar involves the processor rapidly reading and writing information within that dedicated space in the DRAM. It's a fluid, instantaneous conversation between the CPU and the memory. Let's take it a step further. You find our video and press play. Now the computer needs to handle even more data. The video file itself starts streaming from the internet. The data doesn't go straight to your screen. It first gets buffered in the DRAM. A small chunk of the video is downloaded and held in this temporary memory so that if your internet connection hiccups for a second, the video can keep playing smoothly from the data stored in the RAM. At the same time, the operating system is still running in the background, also using a piece of the DRAM. Your music player might be open, your antivirus software might be doing a quick scan. All of these active processes have their own allocated space in this grand digital workspace. This is why the amount of DRAM you have is so important for multitasking. Each open application and process needs its own slice of the DRAM pie. If you have only a small amount of RAM and you try to open too many programs, the workspace gets full. The computer then has to do something clever but slow. It starts using a part of your permanent storage, the SSD, as a temporary overflow area, a process called swapping or paging. This is like your desk getting so cluttered that you have to start putting piles of paper on the floor. It works, but finding anything becomes much slower, and that's when you feel your computer starting to lag and stutter. Having enough DRAM ensures your CPU has a large clear countertop to work on, keeping everything fast and responsive. Let's zoom in even further, right down to the microscopic level. What is this DRAM actually made of? As we mentioned, the fundamental unit of DRAM is the memory cell, and its job is to store a single bit of data, a 1 or a 0. These cells are arranged in a massive two-dimensional grid on the silicon chip, like a gigantic, perfectly organized spreadsheet. Each cell has a unique address, like a house on a street, defined by its row and column number. When the processor needs to read or write a piece of data, it doesn't just shout into the void, it calls out a specific row and column address. This is the random access part of the name. The processor can jump to any cell at any address in any order with equal speed. To access a specific bit, the memory controller first activates an entire row known as a word line. Think of this as lighting up an entire street in our city grid. This action connects all the capacitors in that row to their corresponding vertical data lines, known as Bitlines. At this point, the tiny electrical charge from each capacitor in the row spills out onto its bit line. This is a crucial moment. The charge is so minuscule that it only changes the voltage on the bit line by a tiny fraction. A specialized, highly sensitive circuit called a sense amplifier then detects this minute voltage change. It cleverly figures out if the change means the capacitor was full, a 1 or empty, a 0. Here's the catch, and it's a big one. The process of reading the data is destructive. When the capacitor's charge is released onto the bit line to be read, the capacitor becomes empty. The very act of checking the bucket's state empties it out. It's like measuring the amount of water in a cup by pouring it out. To solve this, the sense amplifier, after reading the value, immediately has to write it back. If it read a 1, it recharges the capacitor. If it read a 0, it ensures the capacitor is fully discharged. This read and restore cycle happens automatically every single time any part of a row is accessed. It's an inseparable part of the read operation. This brings us back full circle to the concept of refreshing. The destructive read process explains why even accessing data helps to refresh it. But what about the data that isn't being actively used? What about the cells that are just sitting there, holding information while you're busy working with a different part of the memory? Those cells are still leaking charge. To handle this, the memory controller periodically pauses whatever it's doing and systematically goes through every single row on the chip, one by one, and performs a refresh cycle. It reads the data and writes it back, not because the CPU asked for it, but just to top up the charge and prevent data loss. This relentless background refresh cycle is the true price of DRAM's simple design and high capacity. Our story begins in the 1960s, a time when computer memory was a bulky, expensive, and power-hungry affair dominated by magnetic core memory. This technology used tiny magnetic rings, or cores, threaded with wires to store data. While effective, it was slow and couldn't be easily miniaturized. Engineers knew there had to be a better way, and many were exploring the potential of semiconductor technology. Early attempts at semiconductor memory used complex designs with multiple transistors for each bit, like static RAM or SRAM, which was fast but took up a lot of space and was costly. The challenge was to create something that was both dense and cheap enough to finally replace magnetic cores as the main memory for computers. This was the technological landscape that set the stage for a revolutionary invention. The breakthrough moment came in 1966 at the IBM Thomas J. Watson Research Center. A brilliant engineer named Dr. Robert Dennard was working on metal oxide semiconductor transistors. While studying their characteristics, he had a flash of insight. he realized that the inherent properties of MOS technology allowed it to build not just transistors, but also tiny capacitors. What if, he wondered, a single bit of data could be stored as a charge in one of these tiny capacitors, controlled by just one single transistor? This was a radical idea. It proposed stripping down the memory cell to its absolute bare essentials, one transistor to act as a gate and one capacitor to store the charge. This was the birth of the one transistor, one capacitor or 1T1C cell design. Dennard's 1T1C design was the epitome of engineering elegance and efficiency. It was incredibly simple, which meant that you could pack an immense number of these cells onto a single piece of silicon. This directly addressed the biggest problem of the time: density and cost. By reducing the complexity from the 6 transistors required for an SRAM cell down to just one, it promised a future of high-capacity memory at a fraction of the cost. He filed for a patent in 1967, which was granted in 1968, laying the groundwork for what we now know as DRAM. This invention wasn't just an improvement, it was a complete paradigm shift that would make powerful, memory-rich computing accessible to the masses. The age of cheap, high-density memory was about to begin. The first company to bring a DRAM chip to the commercial market was Intel, a young startup at the time. In October 1970, they released the Intel 1103. This chip could store 1024 bits, a massive amount for its era, and it quickly became a commercial success. It was the product that proved Dennard's concept was not just a theoretical marvel, but a manufacturable reality. The Intel 1103 effectively killed off magnetic core memory and established MOS DRAM as the new standard for computer main memory. The foundation was now laid, and the stage was set for decades of relentless innovation, fierce competition, and exponential growth in the world of DRAM. The journey had only just begun. The success of the Intel 1103 kicked off a gold rush. Companies in the United States and soon after, Japan, jumped into the burgeoning DRAM market. The 1970s and early 1980s were a period of rapid innovation, with each new generation of DRAM chips quadrupling in capacity. A key advancement came in 1973 from a company called MOSTEC. Their engineer, Robert Prubsting, designed a chip, the MK4096, which introduced multiplexed address lines. This clever trick allowed the row and column addresses to be sent over the same pins, one after the other. This effectively halved the number of address pins needed on the chip, making the packaging smaller and cheaper, a huge advantage that became more significant as memory sizes grew. MOSTEC's design was so robust that it dominated the market for years. However, as the 1980s dawned, the landscape began to shift dramatically. Japanese companies like Hitachi, NEC, and Fujitsu, backed by strong government support and focused on high-volume, high-quality manufacturing, started to challenge American dominance. They invested heavily in new fabrication plants and perfected their production processes, leading to higher yields and lower costs. This led to what became known as the DRAM Wars. Japanese manufacturers were accused by their US counterparts of dumping, selling chips below cost to drive American firms out of the business. Prices for a 64K DRAM chip plummeted from dollars to cents in a matter of months, causing a crisis in the American semiconductor industry. The pressure was immense. By the mid-1980s, many pioneering American companies, including Intel, the very company that commercialized DRAM, decided they could no longer compete in the commodity DRAM market. In 1985, Intel made the historic decision to exit the DRAM business entirely to focus on microprocessors, a move that would ultimately define its future success. Other US firms followed suit, and for a time it seemed like the DRAM market would be completely controlled by Japanese manufacturers. This intense period of competition, while brutal for many companies, was a massive boon for consumers. The price per bit of memory fell relentlessly, making computers more powerful and affordable than ever before. This era of intense rivalry wasn't just about price, it was also about pushing the technology forward. The race to pack more and more bits onto a single chip drove incredible advancements in manufacturing processes, a trend famously captured by Moore's law. The competition forced engineers to come up with new cell designs, like the move from planar capacitors to more complex stacked or trench capacitor structures to keep increasing density. The DRAM wars, though a tumultuous period in business history, were a critical catalyst for the technological progress that fueled the personal computer revolution of the 1980s and 90s. It forged DRAM into the high-density, low-cost product we know today. By the early 1990s, The battle for DRAM supremacy had a new front speed. Processors were getting faster at an incredible rate following Moore's law. However, DRAM speeds were not keeping up. The way computers accessed memory, known as asynchronous access, was becoming a major bottleneck. In an asynchronous system, the CPU would request data and then have to wait an indeterminate amount of time for the DRAM to respond. This mismatch in speed between the fast CPU and the relatively slower DRAM meant the processor often sat idle, just waiting for data. A new approach was needed to close this growing performance gap and allow the system to operate more efficiently. The solution was to make the memory synchronous with the rest of the computer system. This led to the development of synchronous DRAM, or SRAM. The big idea behind SRAM was to introduce a clock signal that would synchronize all the DRAM's operations with the computer system bus. Now, instead of the CPU just waiting, it knew exactly when the data would be ready, based on a set number of clock cycles. This allowed for a much more organized and efficient flow of data. It also enabled a feature called bursting, where a whole block of data could be streamed out after just one initial address request, dramatically improving the speed of sequential data access. The first commercial SRAM chip was introduced by Samsung in 1992, marking another major turning point in our story. SRAM quickly became the new industry standard, and the technology continued to evolve rapidly. The next big leap was double data rate SRAM, or DDR SRAM, which appeared in the late 1990s. As its name suggests, DDR technology was able to transfer data on both the rising and falling edges of the clock signal, effectively doubling the data transfer rate without increasing the clock frequency. This was a massive boost in bandwidth, providing the much-needed memory performance for increasingly demanding applications like 3D gaming and multimedia processing. This fundamental architecture of synchronous double data rate memory has been the dominant paradigm for the last 2 decades. We've seen a steady evolution through successive generations: DDR2, DDR3, DDR4, and now DDR5. Each new generation brought higher speeds, greater densities, and lower power consumption, continuing the relentless march of progress. The story of DRAM, from Dennard's simple 1T 1C cell to the complex high-speed DDR5 modules of today, is a perfect illustration of how a single brilliant idea, when fueled by decades of intense competition and continuous engineering innovation, can fundamentally change the world of technology. Hello again, Gotham here. So we've talked about the history and the big picture of DRAM. Now it's time to put on our engineering hats and zoom right into the very heart of the machine. Let's get up close and personal with the fundamental component that makes it all possible: the one transistor, one capacitor, or 1T 1C memory cell. This tiny duo is the unsung hero, repeated billions of times on a single chip. Imagine a single grain of sand. Now imagine a structure thousands of times smaller than that. That's the scale we're talking about. The design is brilliantly simple, which is exactly why it's so powerful. Its simplicity allows for incredible density, which translates to higher capacity and lower cost per bit. This is the core reason your phone can have gigabytes of RAM. Let's break down the 2 parts. First, we have the capacitor. Think of it as a microscopic, rechargeable battery, but one that can only store a tiny amount of electrical charge. Its job is to hold 1 bit of data. In the world of digital logic, everything comes down to 2 states: on or off, 1 or 0. In our DRAM cell, if the capacitor is charged up with electrons, it represents a logical 1. If it's empty or discharged, it represents a logical 0. That's it. The entire complex world of your operating system, your games, your videos, is built upon this simple binary state, held in billions of these tiny charge-holding buckets. The challenge, as we know, is that these buckets are leaky. The second part of our duo is the transistor. The transistor acts as a gatekeeper or a switch. It controls the flow of electricity into and out of the capacitor. This tiny switch has 3 connections. One is connected to the capacitor. Another is connected to a data line called the Bitline, which runs vertically across the chip, acting like a data highway. The third connection, the gate of the transistor, is connected to a control line called the Wordline, which runs horizontally. The transistor will only open and allow charge to flow between the capacitor and the bit line when it receives a signal, a jolt of voltage, from its specific word line. This gives the memory controller precise control over which cell it wants to talk to. So, the whole operation is like a highly organized warehouse. The capacitors are the storage bins, each holding a single item, a 1 or a 0. The bit lines are the vertical aisles of the warehouse, The Wordlines are the horizontal shelves. To access a specific bin, the warehouse manager, the memory controller, first activates the correct shelf, the wordline. This opens the gates of all the bins on that shelf. Then it looks at the correct aisle, the bitline, to either check what's inside the bin or to put something new in. This elegant 1T 1C structure is the fundamental principle that has underpinned DRAM technology for over 50 years, a testament to the genius of its simple, scalable design. Now that we understand the individual 1T 1C cell, let's zoom out a little and see how these are organized. You can't just have billions of cells scattered randomly. You need a system to find and control each one. This is where the array structure comes in. The memory cells are laid out in a massive, perfectly ordered, two-dimensional grid, just like the seats in a huge cinema hall. This grid is made up of rows and columns. A horizontal line of cells is connected by a shared word line, and a vertical line of cells is connected by a shared bit line. Every single cell in this grid has a unique address, determined by its row number and column number. This grid system is what makes DRAM a random access memory. The controller can jump to any seat, any memory cell, directly, as long as it knows the address. The word line is the row selector. When the memory controller needs to access data, the first thing it does is select a row by sending a voltage pulse down a specific word line. Think of it as the controller shouting, "Everyone in row 24, please stand up." This voltage activates the gate of every transistor in that entire row. This action connects every capacitor in that row to its corresponding vertical bit line. Suddenly, an entire row of thousands of cells is ready to spill its contents. This is a crucial point. DRAM operations don't happen on a single cell at a time. For efficiency, they always happen on an entire row, which is also called a page of memory. The bit lines are the data carriers. These are long, vertical wires that run through the columns of the grid. Each bit line is shared by all the cells in its column. When a word line is activated and the transistors open, the stored charge from each cell's capacitor flows out onto its respective bit line. Now, the amount of charge is incredibly small. The bit line itself has a much larger capacitance than the tiny storage capacitor. So, when the charge from a one cell flows out, it only causes a very slight increase in the bit line's voltage. Similarly, a zero cell causes a slight decrease. The difference is minuscule, perhaps just a few millivolts. Detecting this faint signal is one of the biggest challenges in DRAM design. To solve this, each bit line is paired with a highly sensitive circuit called a sense amplifier. This amplifier is the real magic of the reading process. Its job is to detect that tiny voltage fluctuation on the bit line and amplify it into a full readable digital signal. It compares the voltage on the bit line to a reference voltage and decides if it represents a 1 or a 0. Because an entire row is activated at once, thousands of these sense amplifiers work in parallel, one for each column, simultaneously reading all the bits from the selected page. This parallel structure is what gives DRAM its high bandwidth, allowing it to move large chunks of data very quickly once a row has been opened. The process of reading and writing data in DRAM is a delicate and fascinating dance of electrical signals, but it has one very important quirk. Let's follow the steps of a read operation. As we just discussed, the memory controller selects a row by activating a word line. The transistors in that row open, and the charge from each cell's capacitor is dumped onto its bit line. The sense amplifiers then work their magic, detecting the tiny voltage changes and figuring out whether each cell held a 1 or a 0. At this point, the data from the entire row is safely held in the sense amplifiers like a temporary cache. From there, the controller can select the specific column it needs and send that single bit or a group of bits out to the CPU. Here's the catch, and it's a critical one. The read process is destructive. Think about it. To measure the charge in the capacitor, we had to empty it onto the bit line. The very act of reading the data destroys the original stored charge in the cell. The capacitor is now empty, regardless of whether it held a 1 or a 0 before. If we did nothing else, all the data in the row we just read would be gone forever. This is a fundamental property of the one transistor, one capacitor design. It's like finding out what's in a bottle by pouring out its contents. You know what was in there, but the bottle is now empty. To solve this problem, the DRAM has to perform an immediate restoration. After the sense amplifier reads the value, it doesn't just switch off. It actively writes the value right back into the cell it just read from. The sense amplifier now acts as a driver. If it detected a 1, it uses its own power to fully recharge the capacitor. If it detected a 0, it ensures the capacitor is completely drained. This entire cycle, pre-charge, row activation, sense and restore, happens automatically every single time a read operation is performed. It's a seamless two-step ballet read, then immediately rewrite. This ensures that the data is preserved, ready for the next time it's needed. The write operation is actually quite similar, just a bit more direct. To write new data, the process starts the same way. A row is activated, but this time, instead of just listening, the memory controller forces the sense amplifier for a specific column to the desired state. If it wants to write a 1, it forces the sense amplifier to drive a high voltage onto the bit line, which then charges up the connected capacitor. If it wants to write a 0, it forces the amplifier to pull the bit line low, discharging the capacitor. Even though you might only be changing one bit, the entire read and restore cycle still happens for all the other cells in the same row, effectively refreshing them in the process. For all these operations to happen correctly, everything must be perfectly synchronized, like an orchestra following a conductor. This is where memory timings come in. Timings are a set of rules that define how long the memory controller must wait between different commands. You can't just issue commands as fast as you want. For example, there's a specific delay required between activating a row using the RAS or row address strobe command and then asking for a column from that row using the CAS or column address strobe command. This is called the RAS to CAS delay or TRCD. Similarly, there's a CAS latency TCL, which is the time from when you ask for a column to when the data is actually available. These timings, often seen as a series of numbers like 99924, are measured in clock cycles and are crucial for stability. These timing parameters are essentially the speed limits of the DRAM. They ensure that there's enough time for electrical signals to travel, for capacitors to charge and discharge, and for sense amplifiers to stabilize. Running timings that are too tight or too aggressive can lead to data corruption and system crashes, because you're trying to read a value before it's truly ready. Different generations of DRAM, like DDR4 and DDR5, have different timing characteristics. While newer generations are much faster overall and have higher clock speeds, you'll find that their latency in terms of absolute nanoseconds hasn't improved as dramatically. The big gains come from improved bandwidth, the ability to move more data at once, thanks to wider data paths and clever internal pipelining. This brings us back to the most defining characteristic of DRAM, the refresh cycle. The destructive read process takes care of refreshing data that is actively being used. But what about all the other data just sitting dormant in other rows? Remember our leaky capacitors? If a row isn't accessed for a long period of time, the charge will eventually leak away and the data will be lost. To prevent this, the memory controller has a mandatory, non-negotiable duty. It must periodically refresh every single row on the chip. This is like a security guard doing rounds, checking every single door in a building to make sure it's still locked. Typically, according to industry standards like JEDEC, every row in a DRAM chip must be refreshed every 64 milliseconds. It doesn't sound like much, but for a computer that performs billions of operations per second, 64 milliseconds is an eternity. The memory controller accomplishes this by issuing a special refresh command, which basically performs a dummy read and restore cycle on a row just to top up the charges. This happens continuously in the background. For a brief moment, the DRAM is unavailable for normal read and write operations, while it's busy refreshing itself. This refresh overhead is the small price we pay for the incredible density and low cost of DRAM. It's the dynamic tax that keeps our digital world running. Alright, so we've established that DRAM is the workhorse main memory in our computers. But it's not the only type of RAM out there. It has a close relative, a sibling if you will, called SRAM, which stands for Static Random Access Memory. The key difference lies in that first word, static. Unlike our dynamic DRAM, which needs constant refreshing to remember things, SRAM does not. It holds on to its data as long as it has power, without any need for a refresh cycle. This is because it uses a completely different and more complex internal structure. Instead of a simple one transistor, one capacitor cell, and SRAM cell is typically built from a cluster of 6 transistors. This design acts like a flip-flop circuit, actively holding the data in a stable state. It's like having a light switch that stays in the on or off position you set it to. Rather than a leaky bucket you have to keep refilling. This static nature gives SRAM a massive advantage in one crucial area: speed. Because it doesn't have the overhead of a refresh cycle and its read process is not destructive, SRAM is blisteringly fast. Its access times are significantly lower than DRAM's. It can be read from and written to much more quickly, making it the ideal choice for applications where every nanosecond counts. If DRAM is a busy city intersection with traffic lights and pauses, SRAM is a Formula One racetrack pure, unadulterated speed. This is why SRAM is the memory of choice for the most performance-critical parts of a computer system. It's the memory that keeps up with the lightning-fast pace of the CPU itself. So if SRAM is so much faster and easier to manage, why don't we just build our entire computer's main memory out of it? The answer comes down to two simple but very important factors: cost and density. That complex 6-transistor cell structure takes up a lot more physical space on the silicon chip than DRAM's simple 1-transistor, 1-capacitor cell. You simply can't pack as many SRAM cells into the same area. This lower density means that for the same amount of memory capacity, an SRAM chip would be much larger and consequently much more expensive to manufacture. We're talking orders of magnitude more expensive. A gigabyte of SRAM would cost a fortune compared to a gigabyte of DRAM. This trade-off creates a clear division of labor within a computer. DRAM, with its high density and low cost, is perfect for the large pool of main memory, the gigabytes needed to hold your operating system, applications, and large files. SRAM, with its high speed and high cost, is used in much smaller quantities for very specific high-performance roles. The most common use for SRAM is in the CPU's cache memory. This is a small, super-fast buffer that sits right next to the processor cores. The CPU keeps the most frequently used data in this SRAM cache, so it doesn't have to make the relatively long journey out to the main DRAM every time. It's the ultimate high-speed workspace for the processor's most immediate tasks. Now let's shift our comparison to another type of memory you use every single day: flash memory. This is the technology inside your solid-state drive, your USB pen drive, and the storage in your smartphone. The biggest and most fundamental difference between DRAM and flash is volatility. As we know, DRAM is volatile memory. The moment you cut the power, the refresh cycle stops, the capacitors leak their charge, and poof, all the data is gone. It's a temporary workspace, designed to be active only when the computer is on. Flash memory, on the other hand, is non-volatile. It's designed for long-term storage. You can save your photos, documents, and games to your SSD, turn off your computer for a month, and the data will be waiting there perfectly safe when you turn it back on. How does flash memory achieve this non-volatile magic? It uses a different kind of transistor called a floating gate transistor. This special transistor has an extra insulated layer that can trap electrons and hold them for years without any power. Storing data involves forcing electrons into this floating gate, a process that requires a higher voltage and is known as programming. To erase the data, a strong voltage is applied to pull the electrons out. This is why it's called flash memory, because a whole block of cells can be erased in a single flash operation. This mechanism is incredibly robust for long-term storage, but it has its own set of trade-offs when it comes to performance. The primary trade-off is speed and endurance. The process of forcing electrons into and out of the floating gate is much slower than simply charging or discharging a DRAM capacitor. While modern SSDs are incredibly fast compared to old hard drives, their read and write speeds are still significantly slower than DRAM. Writing to flash memory is particularly slow. Furthermore, this process causes physical wear and tear on the memory cells. Each flash cell can only be programmed and erased a limited number of times before it wears out and becomes unreliable. This is known as write endurance. DRAM, in contrast, can be written to virtually an infinite number of times without wearing out. This is why your computer needs both. They serve completely different yet complementary purposes. Flash memory in your SSD acts as the library or archive. It's where all your programs and personal files are stored permanently. When you want to work on something, your computer goes to this library, gets a copy of the book, the program or file, and brings it over to the high-speed temporary workbench, which is your DRAM. You work on it there, where changes can be made instantly. When you're done and you hit save, the updated copy is sent back to the library for permanent storage. Using one without the other would be incredibly inefficient. You wouldn't want to work off a slow, wear-prone SSD, and you certainly can't store your family photos in volatile DRAM. So, after comparing it with its siblings, where does DRAM truly fit into the grand scheme of computer memory? Its role is defined by a unique sweet spot in the memory hierarchy. The memory hierarchy is a concept that organizes different types of storage in a pyramid. At the very top, you have the fastest, smallest, and most expensive memory, the CPU registers and SRAM caches. At the very bottom, you have the slowest, largest, and cheapest storage, like traditional hard drives or cloud storage. DRAM sits squarely in the middle. It's the crucial bridge that connects the lightning-fast world of the CPU cache with the vast, slow world of permanent storage. It offers a balanced compromise. It's much larger and cheaper than SRAM, and vastly faster and more durable than flash memory. This middle ground position makes DRAM the undisputed king of main memory. No other current technology can provide the gigabytes of fast, rewritable, and relatively inexpensive memory that modern operating systems and applications demand. Think about what your computer is doing right now. Your operating system, be it Windows, macOS, or Linux, needs a large, fluid space to manage all its background processes. Your web browser, with its dozen open tabs, is consuming a huge chunk of memory to keep those pages active and responsive. If you're a gamer, the massive game worlds, high-resolution textures, and complex character models are all loaded into DRAM to ensure smooth, stutter-free gameplay. None of this would be possible with the tiny capacity of SRAM or the slow write speeds of flash. Furthermore, DRAM's random access nature is perfectly suited for the chaotic and unpredictable workload of a modern computer. The CPU is constantly jumping between different tasks, needing a small piece of data from one application, then another piece from the operating system, then another from a background service. DRAM's ability to access any memory location with roughly the same low latency is essential for this kind of multitasking. It doesn't matter if the data is at the beginning of the memory stick or at the end. The access time is consistent. This is fundamentally different from storage like an old hard drive, where accessing scattered data required physically moving a read or write head, which was extremely slow. Ultimately, the choice of memory is always about finding the right tool for the right job. You wouldn't use a screwdriver to hammer a nail. Similarly, you wouldn't use SRAM for bulk storage or an SSD for CPU cache. DRAM's unique combination of speed, density, cost, and endurance makes it the perfect tool for the job of main memory. It is the great mediator, the essential workspace that allows the processor and the storage drive to work together efficiently. While new memory technologies are always on the horizon, DRAM's incredibly well-balanced profile has allowed it to reign supreme in this role for over 5 decades, which is, honestly, a remarkable feat in the fast-changing world of technology. Alright, we've explored the theory, the history, and the internal workings of DRAM, but how do these incredible devices actually get made? The journey from a raw element to the memory stick you plug into your motherboard is a marvel of modern manufacturing, a process that takes place in some of the cleanest, most technologically advanced facilities on Earth. It all starts with a simple raw material, sand. Yes, the same stuff you find on a beach. Sand is purified to extract silicon, which is then grown into massive, perfectly structured single crystals called ingots. These ingots, which can weigh over 100 kilograms, are then sliced into ultra-thin, perfectly flat discs known as wafers. This pristine silicon wafer is the canvas upon which billions of memory cells will be painted. The process of creating the DRAM cells on this wafer is called fabrication, and it is a breathtakingly complex dance of chemistry and physics. It involves a technique called photolithography, which is like a highly sophisticated form of stenciling. The wafer is coated with a light-sensitive material called photoresist. A mask containing the pattern for a specific layer of the chip circuitry is placed between the wafer and a beam of ultraviolet light. The light passes through the mask, exposing the photoresist in a precise pattern. The exposed areas are then chemically washed away, leaving a stencil on the wafer. This process is repeated hundreds of times, layer by layer, to build up the intricate structures of the transistors, capacitors, and the metal interconnects that wire them all together. This entire fabrication process happens inside a clean room, an environment that is thousands of times cleaner than a hospital operating theater. A single speck of dust, smaller than a human hair, can ruin an entire chip by causing a short circuit. Technicians must wear special head-to-toe suits, often called bunny suits, to prevent any contamination. The scale of this manufacturing is mind-bogglingly small. The features being etched onto the silicon are measured in nanometers, billionths of a meter. To give you some perspective, a single human hair is about 80,000 to 100,000 nanometers wide. Modern DRAM manufacturing processes operate at scales of 10 to 20 nanometers, pushing the very limits of what is physically possible. Once all the layers are built and the fabrication is complete, the wafer, now containing hundreds of individual DRAM chips, called dies, is tested. Probes make contact with each die to check for defects. The dies that pass the test are then cut from the wafer using a high-precision diamond saw. Each good die is then packaged in a protective casing, usually a black plastic rectangle with metal pins or contacts for connecting it to a circuit board. Finally, these individual packaged chips are soldered onto a green printed circuit board, or PCB, to create the final product you recognize. A memory module, or as it's more commonly known, a RAM stick or a DIMM, dual inline memory module. The DRAM market is not for the faint of heart. The sheer cost of building and maintaining a modern fabrication plant, a fab, is astronomical, running into billions of dollars. This immense capital investment, combined with the brutal price competition we saw in the DRAM wars, has led to massive consolidation over the years. Today, the global DRAM market is an oligopoly, dominated by just three colossal players: Samsung Electronics and SK Hynix from South Korea, and Micron Technology from the United States. These three giants control over 90% of the entire market, giving them significant influence over supply and, by extension, pricing. This tight control is a key characteristic of the modern DRAM business. These companies don't just sell DRAM for computers. Their products are essential components in an astonishingly wide range of devices that define our modern world. Of course, the biggest application is in personal computers and servers, where DRAM serves as the main memory. But it doesn't stop there. The graphics card in your gaming PC has its own dedicated pool of high-speed DRAM, known as GDDR, Graphics Double Data Rate, which is optimized for the massive parallel workloads of rendering complex three-dimensional scenes. Your smartphone contains a special type of low-power DRAM, or LPDDR, designed to provide high performance while sipping battery, keeping your device running for longer. The reach of DRAM extends even further into our daily lives and cutting-edge technology. The latest video game consoles like the PlayStation 5 and Xbox Series X rely on huge unified pools of DRAM to create their incredibly realistic and immersive gaming worlds. The complex infotainment system in a modern car, which handles everything from navigation and music to driver assist features, is powered by DRAM. And at the highest end of the spectrum, the world's most powerful supercomputers, used for scientific research and artificial intelligence, use specialized high-bandwidth memory, HBM, where DRAM chips are stacked vertically to create an ultra-fast, wide data pipeline directly to the processor. This widespread use means that the health of the DRAM market has a ripple effect across the entire tech industry. Any fluctuations in DRAM price or availability can impact the cost and production of countless other products. Because the market is controlled by so few players, their decisions on how much new capacity to build and when to transition to newer technologies have a profound impact on everyone. From the gamer looking to upgrade their PC to the data center manager planning a server expansion. DRAM is a foundational commodity, a critical resource upon which much of the digital economy is built, and its story is a fascinating intersection of deep technology, global business, and economic power. So, after this deep dive, from the microscopic dance of electrons in a one-transistor, one-capacitor cell to the global stage of multi-billion-dollar corporations, what's the big takeaway? It's that DRAM, this seemingly simple component, is far more than just a number on a spec sheet. It is one of the fundamental pillars holding up the entire structure of modern computing. It's the silent, tireless workhorse that allows your powerful processor to actually do its job. Without the high-density, low-cost, and high-speed workspace that DRAM provides, the digital world as we know it would grind to a halt. The seamless multitasking, the rich multimedia experiences, the immersive gaming worlds, all of it is built upon this remarkable technology. It is the great enabler, the critical bridge between processing and storage. We've seen how its invention by Robert Dennard was a stroke of pure genius, a paradigm shift that moved us from bulky magnetic cores to elegant silicon chips. We've journeyed through the fierce DRAM wars of the 1980s, a period of brutal competition that, while painful for many companies, ultimately democratized computing by making memory incredibly affordable for everyone. This relentless pressure to innovate has continued unabated, pushing manufacturers to perform incredible feats of engineering, shrinking components down to the atomic scale, and packing billions of them onto a chip the size of your thumbnail. It's a story of constant incremental improvement that has delivered exponential gains for technology as a whole. The core trade-off of DRAM, its beautiful simplicity versus its inherent flaw of needing to be constantly refreshed, is what makes its story so compelling. It's a perfect example of an engineering compromise that has stood the test of time. For over 50 years, this design has not just survived, it has thrived, scaling across generations from kilobits to gigabits. It has evolved, adopting synchronization with DDR technology to keep pace with ever-faster CPUs, and branching out into specialized forms like LPDDR for mobile devices and GDDR for graphics. Its adaptability and its perfectly balanced profile of cost, speed, and density have made it an irreplaceable component in our technological ecosystem. Next time you power on your laptop, unlock your phone, or fire up your gaming console, take a moment to think about what's happening in that first second. Billions of tiny capacitors are being charged, ready to create the temporary digital canvas upon which your entire experience will be painted. Every app you launch, every video you stream is a testament to the power and elegance of DRAM. It truly is the unseen hero, the invisible architecture that makes our fast-paced, multitasking digital lives possible. Understanding its journey gives us a much deeper appreciation for the incredible complexity and ingenuity packed into the devices we use every day. The story of DRAM is far from over, but the road ahead is filled with challenges. As we continue to shrink the components, we are running into the fundamental limits of physics. The capacitors are becoming so small that they can barely hold a distinguishable charge. And the transistors are so close together that interference and leakage become major problems. Each new generation, like the move from DDR5 to a future DDR6, requires immense research and development to overcome these physical hurdles. The easy gains of Moore's law are behind us, and future progress will be harder won and more expensive than ever before. This has engineers and scientists looking at what might come next. The industry is actively exploring several next-generation memory technologies that could one day supplement or even replace DRAM in certain applications. There are contenders like MARAM, magnetoresistive RAM, which uses magnetic states instead of electrical charges, offering non-volatility and high speed. Then there's PCRAM, phase change memory, and ReRAM, resistive RAM, which also offer the tantalizing prospect of a universal memory, something that is as fast as DRAM but also non-volatile like flash. These technologies promise to blur the lines between working memory and storage, potentially revolutionizing computer architecture itself by eliminating the need to constantly move data between the two. However, none of these new technologies have yet managed to unseat DRAM from its throne. The biggest reason is the massive, mature, and incredibly efficient manufacturing ecosystem that has been built around DRAM for decades. It is simply so cheap to produce at scale that no new technology has been able to compete on a cost-per-bit basis for main memory. The most likely future, at least for the medium term, is a hybrid one. We might see systems that use different types of memory for different tasks. SRAM for cache, DRAM for main memory, and perhaps a new tier of persistent memory like PSRAM sitting between DRAM and the SSD, offering a blend of speed and permanence. Ultimately, the relentless demand for more, faster, and more efficient memory will continue to drive innovation. From artificial intelligence and machine learning, which require vast datasets to be held in memory for training, to the metaverse and augmented reality, which will demand unprecedented low-latency performance, the applications of tomorrow will push memory technology to its absolute limits. Whether the future belongs to an advanced form of DRAM or a completely new paradigm, one thing is certain. The quest for the perfect memory, fast, dense, cheap, and permanent, will continue to be one of the most exciting and important frontiers in the world of technology. Thank you for joining me on this journey with SoftTech Explorer. Don't forget to like, share, and subscribe for more deep dives.